Okay. So people watching at home are gonna see like they hopefully will hear me and see me, and they'll probably see what we're talking about via this screen right here. So there will be a recording of this. It's probably not gonna be the best of recordings. I'm gonna be walking in and out of frame constantly like this, so hopefully they'll be able to hear me. But this is getting recorded. It says recording right here. Turn it up a little bit higher on the frame. Okay, and probably what we can do is we can get R going, and I might need a Mac person to help me. Let's see if Brian understands how to do Mac on an R. Or is it? Nope. Oh, look at that. And then, oh, look at this. Is this gonna work? Look at that. Oh my gosh, that's huge. View, zoom out. For once we have to zoom out, right? View, zoom out. You know what'd be so cool? If I could have like the Word document open over there and do like 3 screens on this and like type the stuff I want to say to you guys so we don't have to switch between. So you're probably gonna have to listen to me because there's gonna be like a reverse camera view, what's going on here. And so listen up, watch what I type. It might be hard to see for those who watch this again online, but the main thing is the concept. So let's also get a Word document going right here. The exam is fully written. I think it's 7 questions, to which my girlfriend was like, why is it taking you 6 hours to write a 7-question exam? When I told her it was 7 questions. To which the issue is that it's 7 questions, but it's a very long 7 questions. So we're not gonna be able to do that. We'll put the extra. Oh man, I am, who's my Mac people? I'm liking it. You guys liking Macs? You happy with your choice to go with the Mac? It's all right. So look, we go up here. We say we got to do this. We got to do that now to get between. So online, they're gonna have to view that, and hopefully they can see. Problem is, it's a mirror image with what they're viewing. Wish I could mirror image this. So listen up and listen to what I say. Listen to what I type. Those who are watching online, and you know what? Probably better than seeing me is going to be watching the screen. So let's do this so you guys can watch the recording afterwards. Let's go to screen share. Let's go to desktop number 2. Okay, so that looks to be what we're sharing now. Oh wait, give me 2 seconds everyone, because I don't think I'm sharing the right desktop. We'll be started in just a moment. Stop sharing. All right. Share screen. Is that not desktop number 2? Well, whatever I'm sharing, and I think I'm sharing that up there. Keep your fingers crossed if you want to watch this recording. The audio will work, so you might have to listen up to what I'm saying, what I'm doing, or you might be watching me. Who knows? But this is my first time trying to do this in this room with this setup, because usually I use 2 computers to do it, and then I share from the computer where I'm doing all the work. So I'm used to doing it via that, but we're in this room, so we deal with this room. Everyone doing all right? Started 4 minutes, 5 minutes late, but that's okay. Let's get over to doing some work, and let's see what you guys have questions with. What questions do you have? What chapters do you want to cover? What chapters shall we cover? Nothing? Oh, it's great having you guys here. Let's go home. Let's all go home. Good time. I think surely you guys want to hear about something. 7 questions. All right, let's look at some associated command stuff. And so I'm probably gonna have to kneel down here to do some of the code. Hopefully they're seeing it online. I keep saying that, fingers crossed. And I'm gonna have to like literally look between. You can always set up your own markdown file. I always suggest doing that. And you know, first little line doesn't matter. But let's go ahead and insert a new R chunk. Let's go to R. I will say this, the whole test was made using just one of the example data frames. And it has a simple linear model, it has a multiple model, and it has a model with interactions. You're like, uh-oh, wait. So I used one data frame and then I carried it through. I'll even go above and beyond, and I don't think you're gonna figure out exactly the whole test, but it's one I don't think we've used yet. I'm gonna say that. I'm gonna go on a limb and say I don't think we've used it. I'm pretty certain. Yeah, I don't think we've used it, to my knowledge. If it's been used like once, I'm sorry, but it's a data frame we haven't used. I went through, created a simple model, a multiple model, and a model with interactions. So you can think about that. You'll have to be analyzing 3 different models. You can think about all the different things we do when we have a simple, multiple, and a model with interactions. So you need to know how to interpret coefficients, interpret intercepts, look at R-squareds, look at adjusted R-squareds. This is just knowledge bombs right there, like things you should be able to do. So let's go ahead with the start of the semester, a good place to start. Start from the beginning, a very good place to start. Let's pull up. You guys are like, Brian, use a data set we haven't used yet. Now, this one I don't have my ultra settings on yet. On my computer, it automatically loads in reg class, which is a problem if I forget that my computer does that. What should we use? EX3, 4, 5, 6, 7, 8, you name it. Where should we go? I'll use whatever data set you want me to use. I guess it only goes, Do EX1? Which one's wine? EX is what? 4? 3, 5, where's wine at? There's wine, EX61. Okay, wine's got like, wine is a bunch of wines from breweries, and it's for logistic. This is the chapter where we cover logistic regression. Just a little bit of background on this data frame. Whenever you open up a data frame, you usually want to take a look at it, see what's going on. You can see we have some numeric, we have a quality, which I think is good, bad. You can always, there's just some helper tips. If I cough, I'm sorry, I'm getting a little sick again. I always suggest doing something like this, literally on cue. So you can see what's going on here. This is just an idea of what our data frame looks like. Does everyone understand that? We've got high and low quality wines. We've got the acidity of the wine, the volatile acidity, the fixed acidity, the citric acidity, the sugar in a wine. Anyone ever have a late harvest Vignal? It's very good ice wine, which means they harvest the grapes later and they have more sugar. That's on the test. Yep. Density, pH, alcohol. So understand this is just data collected on different wines. Does that make sense of what you're looking at here? I literally mean this whenever you have a data frame. This is not on the test, but literally for your own knowledge, you should look at the data you're analyzing before you analyze it. Whether you do it via this method or you go in here and you click on it and you say, let me just take a look at what's going on in the values to see what's happening. A little bit of background information never hurts. I'm going to sniffle and cough throughout the night. So let's start with some of our associate commands. Reg class is loaded up, so we got the associate command going on right here. And we want to do maybe 3 different types of associations. We've got quantitative associations, and we've got a categorical X, which we can use. If we want to look at the, let's see, residual sugar and tilde, so we're doing residual sugar, tilde, and now we're gonna see if there's a difference between the quality, and please tell me if I make a mistake. I literally have to turn my head every 2 seconds. Data equals EX, and once I do EX6 is it? There we go, that shows up. Always use the autocomplete. And I should get an associate command now, as long as I didn't make any typos. That's gonna make me dizzy all night. And it's not a huge data frame, but it's taking a moment here. If it ever takes too long, you should look down at your console and it'll sometimes ask you if you need to type in Y. A lot of people are getting hit with that on a few homeworks where it says like, please type in Y to continue. And you're like, well, no, duh. I told you to do this, so please continue. You can put in prompt equals false, and I think it even says that right here. I guess it doesn't say it in this one, but if you put in prompt equals false, it won't prompt you. So whenever you run your commands with many or extra, you can put in prompt equals false. So let's see what we got going on right here. Probably best to look at this output first, and we can even open it in a separate window right here, or not. Please open. I guess not. Maybe it did. Who knows? Does anyone else use this button right here? Usually it opens it in a separate window, right? And I guess I'm going crazy tonight. Or who knows? I'm dual screening, doing all this craziness. You could always, let's do one last thing right here. Let's take the command while I crash everything. Let's paste it and bring it down to here. What this will do, as long as the screen is wide enough, randomness, that's from last time. Oh, I've already, Brian doesn't know how to use his Mac. Copy, paste, run. And now it should bring up the plots over here. We might get a plot error. If you're going to plot error, it's because your margins aren't wide enough. It's trying to build a plot in something it can't build. I want to build this over here. That should bring up the plots. It did. Now I can go to the zoom. We can get a better view of what's going on. Or not. Oh, they're all appearing on this screen right here with me. Oh, that's cool. Can I? Yay, let's go to new desktop. Or not. Okay, let's view what's going on right here. Cool. All right, I can finally stand and talk. All right. What we got going on? How do the distributions look? Let's analyze the distributions first. I hate that the high is in the way. When I make graphics, I try to make them look nice. Please tell me at level, there's like 4 tiers of graphics, like 4 rows of graphics. Row 1, 2, 3, 4, what gives you your real inclination on if this data is skewed or normal? Row 1, 2, 3, or 4, which tells you the data is skewed or normal? Which one? Row 3. And what are those? QQ plots for normality. Row 3, do not be confused by row 4, which is our whats. Those are whats? Row 4, the very bottom, are our whats. A lot of people forget what those are. Yeah, it's related to p-values. It's the permutation test. So the bottom row right there, which looks like it's a skew thing going on, is a permutation test. So the reason, so how's that? How do those QQ plots look? Please ask a question if you have it. Like, Brian, what are you talking about QQ plots? I'm talking about these values right here, which are the normal quantile plots, also known as QQ plots, also known as plots for normality. So if you are any question, please ask. How do those look? Good, bad, in between? What do you think? They look pretty bad. They look pretty bad because they do not follow the red line that closely. Especially at the low end, we see a big departure from normality. And you can kind of see this in our distributions where you see some outliers and a little bit of skew. As we said, and you don't need to remember this, but if it's pushed to the right, it's skewed to the high. If it's pushed to the left, it's skewed to the low. We covered that a long time ago, but the big thing to remember that really you only need to remember is if that QQ plot doesn't follow the red line, it's not very normal. Does that make sense? So with that in mind, we see here that these are not that normal. We need to look at this first to make decisions. So what will I analyze here, means or medians? The decision will be medians because we see there's a skew to the data. You can also see, especially in the high distribution, that the mean is higher than the median. Does everyone see that star that goes away from the dot, New York accent? Right there, that is the mean, that little star right there. The median is the line. These two are very close. This one has a little bit more of a skew, denoted by its harder push to the right here. There's also a bit of bimodality, as denoted by the bump here and the bump here and the swoosh there. You don't need to get that crazy with it. The big thing with the QQ plots, if it's a straight line, it follows normality. If it has little problems, whatever. But with these, I mean, the bottom of it and then that, there's problems. And then do these histograms look normal? And the whole thing just screams at you, and I'm glad we did this example. It screams at you, you should analyze the, say it again, medians. Very important decision we made there. Switching over to the output. When we look at the output right here, we have the means and the medians. As we see the means for the high, everyone notice how the mean for the high is much higher than the median, as we noted, because we could see the star difference. The mean and the median for the low are not that different. We're looking at this row right here for means and this row for medians. So what we see, and I hate that the p-values do this, the p-values for the associated is means p-value and medians p-value are associated for these ones right here. What we see here is that there is a difference between the medians, because that's what we wanted to analyze, a difference of 2.85, is that correct? Please someone check my math. 2.85, that is correct. There's a difference between 2.85. All I did was subtract those numbers. The difference of 2.85, when we talk about it, that would relate to the what of the difference. When I say there's a difference between those two medians of 2.85, I'm talking about the what here. The discrepancy is a metric based on statistical analysis, based on actually these distributions right here. Do you see how the medians, where's our medians? Right over here. That red line right here is actually about where like 98 is. That's where the discrepancy occurs. And so if you view back here, that 96.57, that's where it occurs on the permutation test. And this relates to mixing up the numbers and seeing if we see a discrepancy as big of, and it's a calculation thing that we don't have to know everything behind. We do need to know that permutations mix up the data set so they're completely at random. But what we see right here is that this difference of 2.85 would speak to the what significance? This difference of 2.85 speaks to the, I heard it, practical significance. If we're talking about the actual difference we observe, It would be practical significance. Now, here is a big thing. We can't get to practical significance yet. What must we first talk about? Statistical significance. Because if something is not statistically significant, we're saying that it could be by. So why would we make decisions on something that could be by chance? I don't care if the difference is 100 or 50 or 5 million. You know, it's like the GDP of countries. That's big numbers, right? So a difference of 5 million between countries could be a difference that could happen by what? Chance, because countries' GDPs are very high. But a difference between 5 million of my salary to someone else's, do you think that difference happens by chance? No. So we need some way to scale that and talk about the probability of our difference. And the probability of our difference happening by chance, or something more extreme than our difference, would be the what? It is the p-value. Specifically, we said that we are analyzing medians. I want to make sure that this is very clear. We are analyzing medians here, and we need to know that if we're going to talk about this difference and its statistical significance, we need to look at the p-value for medians. When it comes to talking about, can we use this difference? Well, that's practical significance, and one, it might hold some practical significance because it is statistically significant. To get to practical significance, you have to go through statistical significance. Practical significance comes after statistical significance. So with that in mind, let's talk about the difference of 2.85. Well, this is the sugar level of wines, and maybe it's like in, I don't know, milligrams of sugar they find in 1 cup of wine. And when you think about this, I would state, and this is just a random problem we did that I've never done before. I would say the difference of 2.85 between the low and the high quality wines is almost double, and I would maybe fine, I would say 66%. Does everyone see how I'm saying it's almost double the high? Do you see? Because if it's a difference of 2.85, that's like 70% of the difference. That's a lot of a difference. So to say, and I would actually figure that out, I would divide the difference over the high. What is 2.85 divided by 3.875? Well, I've got R. Let's go right here and do 2.85 divided by, I am one of those people who forgets that R will just solve it for you. Well, that's not right. What did I type? I'll hit up. Oh, haha. You should always have a guess. I'd say 0.71. 0.735. So you should have a guess. I always make a guess so that if I mess it up like that, I'm like, that's not right. That's an error. So 73.5%. The low quality wines have 73.5% more sugar content. Does that seem like a big difference to you? If I told you your cereal has 74% more sugar in it than someone else's cereal, all of a sudden you're like, wow, that's a lot. And it all matters. Like, what if you made 10% more in salary than someone else? Like yearly salary. Would that be a big difference? Probably. If it was statistically significant, probably like, hey, 10% more in salary. What if, a parachute has a 1% higher failure rate than another type of parachute? Like one has a 0.0001 failure rate, and then the other one has a 0.0101 failure rate. Now you're like, okay, well, that's a lot more. 1% is a lot. Do you see how every time we talk about practical significance, we need to do what with it? We need to talk about it in context. You need to somehow come up with your own reason why it is or is not practically significant. So for me, with this problem, which is one we just came up with, this would have been a great test problem. Is this practically significant? I would think most people should answer for this problem, yes. The low quality wines, and you could mention the difference, have 2.85 more sugar content than the high quality wines. I would go a step further and say that is 74% more when rounding, which is a lot more sugar to have on average, or for the median wines, because it's medians we're comparing. That seems like a large difference, telling me that the low quality wines have a lot more sugar. And one, this didn't have by chance. That's like crazy. If you talk about practical significance, one, mention the difference, and then two, give some insight into why it matters. Like, oh, this is 74% more. That's a lot more sugar. So that's got this. We see that our intervals to look at the median, do they come back conclusive or inconclusive? To look at the difference between the medians. Are those intervals conclusive or inconclusive? What are they? They are our intervals. Our interval to look at the median to see if the median has a significant p-value is it conclusive or inconclusive? Conclusive. Because why? Because 0.05 is not in the interval. If 0.05 is in this interval, our interval would be inconclusive. So we specifically need to look here. Our test is conclusive. We are pretty certain that we have significant results here. I mean, our interval is very low. And if 0.05 was in there, what would we need to do? It says below. Do what? Increase permutations. If I asked that question on the test, I probably would not include that because it literally says if 0.05 is in the range, which is our inconclusive, if you are above or below that, not significant, significant, the changeover right there. So that would be the issue, is if we have 0.05, we can't really make a conclusion about significance. So we can increase the permutations right there if it is in there. That's got this output. Like in the Mac, like in the Mac. What do you guys want to look at next? Do you want to do correlation on this? Yes? No? Okay, let's do correlation next. I mean, that was a pretty good review of that topic, right? Please ask questions if you have them. I'm just going to go through here and do examples with review. I mean, they're just as good as any other question I could ask. Let's do it. Let's change. What do I need to do here if I need to change correlation? Boop. Change that. And one of my favorite tricks to get something is to go to names. I should just trust myself. I'm going to try to do this and not look. Good. And then I need to look to get this. So we're doing residual sugar. Let's look at volatile acid. I wonder if there's a relationship there. I have no idea. Okay. I have to look if I'm doing this. And here we go. Y tilde X. We're seeing that the volatile acid can tell us anything about the residual sugar. Is there a relationship between the two? Is there an association? Same sort of idea. So let's run this right here and see. Wow, that's a mess of data. Well. We've got skewed data frame right here, skewed data frame right there. Those are called just side histograms or histogram borders. We can't calculate the exact p-values for the Spearman with the rank. Whoa, this is interesting. Do you see it? The p-value for this. So this is very quick right here. This tells me that there is some sort of nonlinear monotonic relationship right here because the Spearman comes back significant. Spearman is relationships that are monotonic. They go like this. Does everyone remember that? Spearman goes in one direction, meaning monotonic, where Pearson is only linear. So if the Spearman picks up on something that the linear doesn't, then there's not really a good linear association here. There's some sort of Spearman. And maybe it's that it goes through the data like this. Actually, our results were positive Spearman. So there's some sort of bend this way. Why? Do what? Yeah. Quantitative variables associate command. So residual dot sugar, volatile dot acidity, data equals EX6.1. Be careful. Some people sometimes put the dollar signs before it here. That'll cause problems like visualize model. A lot of problems. I'm allergic to you guys. I'm sorry. Because I can't give the test this week. I'll have Dr. Petrie give it. He'll make it harder. Everyone got it? No? Good? Yeah. This data didn't turn out so pretty in here. Let's see. So we do have, as I kept saying, that we have a Spearman relationship right here. The value of the Spearman rank correlation, this is the p-value of it explicitly. Should give, For some reason, sometimes the output, especially with these small screens, is not coming up so nice. So look at it down here. As I said, Spearman rank correlation is saying that as the rank of volatile acid increases, the rank of residual sugar increases. We also see that the confidence interval to estimate the true p-value is conclusive. And we see that the Pearson comes back as conclusive non-significant. So the p-value for the Pearson to detect a linear relationship, remember, this is pure linear relationship right here. Pearson is just linear, where Spearman can do monotonic, non-linear. And that's the point. And funny enough, this is This is a great example. Frankly, I wish I'd put this on the test. We're just coming up with all the good test questions. This is kind of a cool one right here because you don't really have evidence of a linear relationship. You have a non-monotonic, you have a monotonic nonlinear. Got ahead of myself. So there has to be some sort of positive thing going in here. The data is so clustered, it's hard to see. It is very weak, but it is statistically significant. And it could be due to outliers, and I'm going to plead ignorance on this. I know how to run the influential plots, which is something we can get to in just a little bit. I can run the influential plots for just regular linear regression, but, well, actually, wait. I just said something wrong. Spearman is not going to be influenced by outliers because the rank of the highest outlier can change and go up. Spearman is impervious to outliers, and that's why we use it. So frankly, it might be those, and think about if you were to have a line going through here. Like if you had a line going up, this point right here would be extremely large in at least what? This is another great question. Ooh, I can hit a bunch of things with this. What is that point going to be very large in? It has to be large in this where it's at. Leverage. That point is extremely large in leverage, and what does it mean to be large in leverage? Far away from the mean of x is perfect definition of what it means to have high leverage. This point right here is extremely high in leverage. It is frankly, I would say it has to be the highest leverage point, right? Mean of the x's, unless mean of the x's were up here, which it's obviously not. It's probably in here somewhere. The mean of the x's I would estimate to be right there. You can even find the mean of the x's if you super want. You just go here, you go summary, say, well, what is the mean of the x's? And y tilde x, so we have ex7, is it? ex6, and then $sign, and then we're doing volatile acid, so let's run that. Mean of the x's is 0.3. Yeah, I wish I could. I know a way to do that. Let's do this. Let's do plot, and then let's do this. Let's go ab line. What do I want? I want a vertical. Vertical equals 0.3, comma, col equals red. And there we go right there. I wonder if I do, I'm gonna try something I never thought of. Comma CEX, that's point size, but I'm wondering if CEX will, nope, it's not a command. I'm not gonna worry about the ab line, you can see it. But I was hoping CEX was also a command for ab line. I don't know how to make the ab line thicker. It's probably something simple like thickness equals or size equals. But for our purposes, that works. What it means to have leverage, we're kind of switching over to a newer thing we talked about. What it means to have leverage is to be far away from that red line. That red line at which we are viewing is the mean of the x's, and I put it in at 0.3, but that's close enough. Visually, you can't tell the difference between 0.029 or 0.29 and 0.3. So I put it in right near there. So that is the mean of the x's. And this point obviously has ridiculous leverage. Going a step further, let's go to a newer topic here because I love this. Let's take this plot. Because when I do this stuff, I just have questions. Let's create a linear model. All I'm going to have to do to create my linear model is take my last command and change it to LM. Does everyone see what I did right there? I don't want ab line on there because ab line, this is a whole just to make it a model thing. This is how you can kind of walk yourself through. I'll pause on this for a moment. I'll throw some New York accent at you. Pause. Hair's getting so long. Everyone good? So let's take a look. Well, not yet. Let's look at the influence plot of this. And let's run it with M to hit M. What? No, what? Okay, good. This is a mess. Wow, this is one of the messiest influence plots I've ever seen. Why did those points back there? And actually, let's run the whole, we're gonna get a plot and get a summary. Let me take out this summary. Let me take out this summary of the wine. And let's run the block and get the two pictures on here. I thought it showed both pictures. So I don't know how this works. So I want to point out specifically this point right here, with that point, and frankly, we can do one more thing. Watch this. Put in here, ab line, and this would not knit properly now. But does everyone see I'm ab lining M? Oh. And there's the line. Let's make it a color. Col equals orange, UT orange. Okay. So the red line is the mean of our x's. The orange line is our regression model, which does have positive linear correlation, which is not statistically significant. But my theory was that this point was highly influential in pulling down because, one, I knew my line had to go up. Does that make sense? How did I know my line had to go up? Because the correlation was positive. So I knew my line had to go up. So I figured this point had to be below it, pulling it down, because cluster of the x's look there. This line has to go there. This point right here, that has to be, is it not? It's not, I guess. Because when we look at the highest, yeah, do you see that right there? That humongous circle. This is the messiest influence plot I've seen in a long time. This point right here is that point we were just viewing a half second ago that is far down below the line. It's this right here, because it has the second highest leverage, agreed. It's the second farthest away from this red line, and it also has a decent residual. But funny enough, really? All right. Hey, wait, nice job. Oh, you can actually see it. I think it's because it's scrunching the screen on this. That looks more like what I see all the time. Wow, those residuals, this is such a weird model. Oh, it's because that all cluster. You can see how everything folds over on itself. You just have a lot of points near the mean of the x's. And all of our residuals, deleted studentized residuals, are the high ones. So these points right here are the leverage ones that are actually creating the upward slope. Do you understand that? These points right here are pulling the line upwards. That's the influence they have. These are pulling the line back down. None of them meet our criteria. And even this one is not as big as, with all of its leverage, as big as these ones. So although you can't see it, how many quadrants does the influence plot usually have? I mean, there's really only how many quadrants? I'm going to have to show you another one to show it properly. How many quadrants? Well, you might be saying how many quadrants there are, but how many quadrants where there's influence? I don't think I said it properly. I think someone just said it too. All right, so the quadrants would be this one right here. This quadrant, anything in here would get marked with an X. Does that make sense? Because these points have what? If they're up here, they have a deleted studentized residual of bigger than +2. Deleted studentized residuals bigger than +2 only occur about 2%, 2.5% of the time, 68, 95, 5, 2.5. Does that make sense? So 2.5% of the time do we get a deleted studentized residual outside of above 2. 2.5% of the time do we get one below -2, which, funny enough, this model is just such a messy model, which you get a lot of times, just weird models. It doesn't have any deleted studentized residuals that are below -2. Weird, and that's just weird in of itself. Something tells me, we'll do a check regression on this model. Something tells me the check regression is going to come back really bad. Because if it looks like this, that is not normal residuals. Because think about it. The residuals, we should have residuals down here. Because there should be a quadrant. I want to make this clear. We can't see it in this graphic, but there should be a quadrant right here that would start. What does this line represent right here? Points that what? High leverage. So they're on the high side, right? Careful. Yes-ish. So points above this line are on the high side. Points above this line, they don't have to be. High leverage means they are far from the mean of the x's, high or low. Does that make sense? Because if you take the graphic and fold it over onto itself, that's what we're doing when we do this, is that line right there would be equivalent. We have to go back to our previous graphic. That line right there would be the equivalent of taking this and finding a point right here, like a line right here and a line right here, and then folding the graphic on top of itself down the mean of the x's. This red line right here on this graphic, that red line is 0. It is when a point has no leverage. A point with no leverage is on the mean of the x's, and I guess it would technically be right there. So those are points with no leverage at all. Every single dot you see on that red line we created, Those are points that have no leverage. And actually it would be technically impossible for them to have any influence on the slope. They would literally just pull the line up or down. They would move the line up or down just like a pulley on it. Now, if they're a little bit off, they could have influence if they have a ridiculous residual. But if you notice, the dots are generally smaller when you are really in close. They need some leverage and some residual. There should be two quadrants. It's just that we don't see the bottom quadrant down here, the top right and the bottom right quadrants. And that's when points have outside of -2 or +2, and it's when they have above a set leverage. I don't make you guys memorize the formula for the test. 2 times k plus 1 over n. You don't memorize that. I mean, software, does it for you. So it's more important you know what leverage means. So what was I going to do next? I had an idea. Check regression. Please ask questions if you have it at any time. Check regression is so important, and I see so many people mess this up. You guys are like, Brian, this is the easiest thing we do. It seems like it, but a lot of mistakes. This will look bad. Normality is going to fail, right? Yeah, normality. That was a given. And I say fail. This is where people mess up. They say, woohoo! P-value is below 0.05. Is that good or bad on a test, on a check regression? Bad. Because what we assume, if you go by classical statistical methods, which we use like permutations, we use a lot of the newer stuff in this way of doing it. People don't write out a null and alternative these days. They understand what it means, but we're assuming what the probabilities mean right here. What we see right here is that we assume our residuals have a normal shape. But then we see the probability of getting our shape of residuals given the shape was normal. And what this tells us is the probability of our results or results more extreme given our residuals were normal, our normal is what? Very bad, very low. And look at the normality of our residuals right there. And that's what I said, we're way too built up on one side. So that shows the problem with the tons and tons and tons. Look at this. Does that look like a normal curve to you right there? We had way too many low residuals. That's what we saw right there. We had way too many just build up, or excuse me, we have too few low residuals because we didn't have the negative ones. We had the right skew to it, which you could see, you saw the influence plot a moment ago. But you remember how it only stopped at about -1? Do you see how this graphic right here goes to about -5 and then the high end is much higher? Because we had the high residuals, we didn't have the low. So it's built up, it's a right skew. And look at this once again. If it's right skew, the QQ plot's pushed to the right. You don't need to know that, but it's just kind of neat. It's like, oh, it's right skew. QQ plot's pushed to the right. So we do not have normality of residuals. This is a weird block. I do not think linearity is our biggest problem. As shown by linearity has the highest p-value, but still, do we pass or fail the linearity of the model, which is just one variable right now? Pass or fail? Fail. Do we pass or fail equal spread? Fail. Do we pass or fail normality? Fail. All these are bad. They all get an X. So now we go over to, well, let's slow it down. It's on there. I'm not going to put these helper things on the test. So step 1, look at the p-values. If any of them are below 0.05, we fail that particular one. Does that mean we're done? No. What do we do next? Look at the sample size. Our sample size here is what? Larger than 25. And it really doesn't matter if it's 25 or greater or larger than 25. If you had 25 exactly, it'd be like, I don't know. Decide what you want to do. These are all, kind of guideline things. Frankly, if you had 24, you could probably look at it. But 25 is something we've all kind of agreed upon. It's kind of like the 0.05 standard. Is 0.051 like horrible, horrible, horrible? No, but you get into iffy world when you talk about that stuff. So watch out. 25 is when we say, okay, if it's greater than 25, let's actually look, because these tests can be overly sensitive. It gets into a topic of statistical power, which I would talk about in class, but tonight's review, so let's just go to the graphics. So here we are with the graphics. And we said first, we looked at the linearity. And I said linearity is not our major concern. That line does look to go through the center of those points. Linearity was the highest p-value, still failed. I'm not really worried about linearity here. Second one was equal spread. I do see some issues of equal spread up to about here. We really don't have a lot of data in the model after this point, but I do think equal spread is a slight concern to me. But my biggest concern is the residuals as noted by this is -5 and this is +15, and look at all the 10 and +5. We have a lot of high residuals. It is a very right skew. Good model, bad model, chuck it. What do you want to do? What do you give this model? A to F. Might get an F+, but that's about as high as I'd give it. It gets a 59. Nah, I don't know. It gets a 50. It did very poorly. I mean, also, here's the total end of it. It's not even statistically significant. We saw that to start. Everything we're doing here is based on chance. But we can still analyze it. We can still look at it. We can still look at the assumptions. But everything we're seeing right here is possibly due to chance. When we run the summary on it, I think the p-value comes back as like 0.23. So everything we just looked at was probably by chance, and hence why it looks so horrible. And p-value, 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 multiple r squared. Why am I not seeing p-value? There it is. With a different format, I get kind of confused at where things are at. Also, the p-value for the model and the p-value here are the same because the x variable is the model. In simple linear regression, the p-value for your model is the p-value for your x variable. So you notice they coincide. How about we go to a multiple regression? Or let's do this. I've kind of taken the review where I want it, and I've definitely mentioned things that are on your test. I know that for certain. What would you like to hear more about right now? What would you like me to do? Show? Because we've definitely talked about a lot of things that are on the test. Question? I've seen all different things. I mean, interpretations are key. I mean, that's a big hint right there. Interpretations are key. The slides have a lot of great interpretations. You want your interpretations to be in context and to be strong, to make it clear to the person you know what you're talking about. If there's like, you remember the football one where it had like yards in 100 or whatever? Make sure if you see something like that to talk about that. I've written up the whole test and the whole grading key for my graders. Like I've done everything today. It started at like 9 o'clock and finished up about 5. So the whole test is written, the whole grading key is written, and it has a lot of specifics, and even says like, it's out of 200 points, so divide by 2. There's a 10-point question 5 that says, like it's an interpretation. I don't want to get into more than that. You'll see it on the test. But, it's like 10 if near perfect, 7 if some mistakes, i.e. context problems with what they've written, 5 if they give a good explanation, 3 if they give, or maybe 2, I think it was 2 if they do it like we did in Stat 201, don't do that. 0 if they just give the value. So literally when it says interpret this, and you might be smart enough, I'm not going to say what it is, and I will not confirm or deny anything, but it's something we talk about in Stat 201, you need strong interpretations. Someone's going to be like, Brian, I wrote down what we used to say, and I'm like, well, that got you 2 points because you remembered something from a class that you're not in anymore. So we're more exact in this class, and we're very thorough with our interpretations. I think have I said what it is yet? Usually I'll probably do a 50-50 again, which here's the thing. The take home is your chance to be all super serious about it. So this is a very, very quick 2-3 minute talk on the take home. Please take the take home as seriously as possible. For most people, it's their higher grade because the test is there is the range of difficulty of questions that simply asked if you understand what a VIF is. I mean, if you understand what a VIF is, those questions there's a true or false or 2 on the VIFs. I'm throwing out what things are on the test. You're like, VIF questions, true or false. You write it down. But, simple, there's knowledge-based questions. But then there's application questions that the last question on the test is a very, very good math question with a simple answer. And if you understand it, it's very simple. But you have to know the concepts. And I think a bunch of people will get to the last question, which is only about 3 points out of 106. And they'll just have no idea. They'll be like, we never learned this. But it deals a lot with what we talked about. And there's just a few. I kept it to some questions are hard, some are easy. If everyone fails the test, it's either a fault of mine or who knows, or all curve or who knows. But once again, the in-class is harder. Dr. Petrie, when he teaches the class, usually sees about somewhere between a 65 to 70 in class. The take-home usually has about an 85 to 95. You average the two together, you got a 90, you got a 70, it pulls it to the 80s. So high 70s usually for the test. But it's possible to ace both. And Dr. Petrie usually touts that no one ever gets 100 on his test. So this is meant to be a tougher test. And hey, it's today, and the earliest people are going to take it is on Wednesday. So more questions. So that's what, please take the take home so serious. And also don't cheat, don't cheat, don't cheat. But take the take home as seriously as possible. Has anyone completed the take home or gone really far into it? How'd you find it? Yeah, you just have to be careful. So you've completed it. What did it take, 2 to 5 hours? Yeah, it's not that bad. It's a review of all your old assignments. It's just to see if you can do the R work. So it's not that bad. You just have to be careful. And you have all the notes in front of you. It's very possible to make 100 on the take home. Also, you get points for just entering in your student ID number. That is a question. You do get points for that. Problem is, if you make a mistake on that question, you pretty much fail the take home. So if you see something wacky, please talk to me, but wackiness could be a problem that you cheated. Just talk to me if something happens, especially if you didn't cheat, you don't have anything to worry about. Okay, more questions about the test. What we got? You guys want to do a multiple? Is that what we're on? Take this to the next round? Okay, let's do it. This is better with the light on. All right, let's do it. Let's do multiple regression, and let's go here to call our model M multi. Let's save into it. Let's call an LM function. Doing this, I don't know the names of the variable in this data set. Let's do residual sugar. You know what? Here's how you make and figure out what you want to do. You run the all correlations command, and we want to predict residual sugar. Cheat even more. You go to EX7, EX6, $, residual sugar, and then you delete that off. Oh wait, I'm forgetting the syntax. Not totally forgetting the syntax. Well, no, this works. You want to tell it do the all correlations to this data frame. You want to say interest equals, and you need to put this in quotes. Something a lot of people don't know. Double click it, or single click on the Mac apparently, and then put it in quotes once it's highlighted. All you gotta do is select the quotes, nice and quick and easy. So now when we run the all correlations, as long as I have everything typed in correctly, we should see all the correlations, and we get it in 2 pairs because the screen's small. It's not, it's gonna be way off. Okay, here we go. Oh, variable 2, nice. I could have sorted it. Will this let me sort? No, of course it won't. We can look at p-values. This is our strongest with alcohol. Oh yeah. Is it, wait, it's negatively associated. That's interesting. So it's because the yeast die quicker when there's sugar. Does anyone, any alcohol people here? Oh. Did anyone see the thing they were doing on Ped Walk on Friday where you had to pour the alcohol and figure out how much the shot was in there? I got it exactly right. That's my claim to fame right there. So let's go ahead and get alcohol in here. Let's do some interesting stuff. Let's take the second highest one, which is total sulfur dioxide. That's salts. So we need an M multi right here. Is sulfur dioxide salt? Is that what wine's got in it? It's got salt and alcohol. Just take some rubbing alcohol and some table salt, and you can mix up some wine. Okay. Do what? I'm grabbing the 2 highest just because I'm hoping to see some stuff here. Do what is higher? Oh, holy Jesus. The p-value was so low, I didn't see it. I should have. Wow. Okay, so what one are we going to remove? You guys pick. Let's do the 2 positively correlated. So I need, yeah, I didn't see that because the p-value was 0, 0. I mean, that is, yeah, apparently sugar and density. I guess sugar makes it heavier. Does that make sense? So very, very correlated. More sugar, heavier. And since it's positive, sulfur and there. You might see some interesting stuff. Wow. Okay. So we almost got our M multi completed here. I could have done it with the other ones. There was no rhyme or reason except me trying to make a model with some variables that have some good correlation. So there's our M multi. Just you know, figuring out some stuff, little data investigation. Type M multi, and this will appear, but we'll wait for it. Let's see what happens here. Everything's significant. Cool. You know what? What was that other one called? I want to hit the jackpot and make some examples here. Let's throw in one more here. What was the other one called? I can pull it back up. What was the negative? What was it? Total sulfur dioxide. Yeah, I remember that one now. Okay. So let's put it in here in the back. What am I trying to do by adding in a whole bunch more variables and being like, oh, that's significant? What am I trying to do, for an example? Does anyone know? Why am I adding in more and not wanting them to be significant? What do we got? Oh, p-values around there? Oh, man. Let's throw in, all right, throw in 2 more and then we're done with this and let's start reviewing it and seeing what we get. So now let's get in the next 2 correlated variables. Let's just start building a big model here. The next highest correlated is pH, correct? Or wait, free sulfur. Yes. Okay, I think we're done with that. What? Someone surely knows why I'm happy, why I'm like, okay, free sulfur and total sulfur. Please explain to me why I'm happy for the examples I'm constructing right here. Probably, yes. And why are they explaining residual sugar in the same way? They're very related to each other. So cross your fingers and, my gosh. Well, let's try pH and then call it quits on it. Was pH lowercase p, capital H? Fingers crossed. Man, this is one heck of a model. All right, well, we'll deal with what we got here. It's a good example. We'll just talk about why it is the way it is. Okay, let's remake the output so it looks nice. Okay. Let's start. We haven't done any interpretation yet. We got the output looking nice right there. Where is the significance of the model? Where is my model significance on this page? Where's the significance of the model? I think there was a homework question that asked this, right? It's like, what's your significance of the model? I think is that on the take home? That might be on the take home. Where is your significance of the model? Where? Nope. Intercept is one of the most useless things we have related to the naive. Don't worry. Sorry, don't worry. You got like everything right tonight. Okay, that is the percent of total variation explained in sugar, residual sugar, by these X variables in the model. Ah, look what we got right here. Nice job. Yeah. You got it. I like it. Everyone knows I love when appeals speak up in class. That's what makes us learn. See, now if that's on the test, which it could be, you don't forget. So the p-value of the model is related to the F statistic because this model, oh, this is so cool. This model explains almost 3,000 times more variation than we would expect to be explained by random chance, given that there is no association. 3,000 times. I'll give you $1, and then I hand you a cash bag of money. So, or I just give you 30 $100 bills. You're fine with that too, though, right? Well, was that a lot more than you were expecting when I said I'll give you $1? Like, you lend me $1, I'll pay you back, and I pay you back $3,000 or $2,980. So that's like a lot more than we expected. So the F statistic is observed over expected, specifically O over E, for the observed amount of variation we saw being explained over the expected. Now, you can always think of the expected as 1, because if it's 1 over 1, then we observe what we expect. Does that make sense? So how much bigger than it was than the expected is 2,980 times, which is relatively 3,000. You know, slice some hairs or cut some hairs right there, or split hairs, that's what I was looking for. Basically 3,000 times more variation is being explained than we expected due to random chance. Do you think this model is significant? Ridiculously significant. Ridiculously significant. So we also see, wow, this is probably why this is a data set. We'll use it later on. This data set is so good. I've never done this with this data set, where 84.69% of the variation is explained. And this model is very good. Why is this model very good? And why every time I was adding in variables, they just kept on coming through for me? Why? And why am I not even thinking that I have junk variables in here? Yes. So when you do model comparison, I'll answer in 2 seconds. When we do model comparison, if I had watched the R-squared adjusted, and I want to compare 2 models, I should maybe look at the R-squared adjusted, or what other measure could I look at to compare 2 models to see if one's better than the other? Residual standard error. And this one only misses the sugar by about 2. The average miss of the model is close to 2 when predicting residual sugar. No. So it has nothing to do with the miss. It's amount of variation we explained with the model. So it's the observed variation we explain. I know it sounds weird to say observed variation we explain, but it's the amount we observe being explained, like the sums of squares explained, over what we would expect due to random chance. So due to random chance, we have an E on the bottom. That's what we expect, which you can think we expect 1, because it would actually be a number what we expect, but to standardize it is to say 1. Does that make sense? Because it could be 10. If we expected 10, what did we observe? If we expected 10, what did we observe then for this model for the amount being explained? If we expected 10, 29,800, which is how many times bigger than what we expected? 2,980. And that's what it means, is we observed 2,980 more variation explained than we expected due to random chance. So it's not the variation we are observing in the model. It's not saying there's a whole bunch of variation. It's how much we explained. So I know it's another E word. It's the observed amount of variation explained over the expected to be explained by random chance. And if you standardize that to 1, you could say we observed 2,980 times more variation explained than we would expect due to random chance. So we explained way more than we would expect due to random chance. And as the F gets bigger, the p-value gets smaller, because it's less likely that you would explain a whole bunch due to random chance. Explaining a lot due to random chance is not likely because it's random chance. Question? So the RMSE also stands for the root mean square error. Someone was in my office and I explained this. Were you? No? So, yeah, you came in and asked why it was root mean. Yeah. So you asked, why is it root mean square error? And it's so cool. Because what does error mean? Error means residual. What does mean mean? Mean means average or typical. What does square mean? When you think about it, we're doing the squares, right? So like a sums of squares. But can you just square something and leave it squared? If you square something, you what it? Root it. Root, mean, square, error. Error, residual. Root means taking back the square you did, and mean means typical. Root, mean, square, error. I should have maybe said that in class, but we oftentimes call it by its other name, which is simply what? The residual standard error. And we think of standard errors because we see a lot of standard errors. We don't see a lot of RMSE. That's a specific thing for the root mean square error, which is the typical miss of the residual. We usually see residual standard error because when we talk about the standard error of a coefficient, that is our what in a coefficient? Our basically, we'll say that in a second, it's our uncertainty, right? And we use not to, because it's no longer standard deviations, it is standard errors now, because it's based on samples. Standard deviations are kind of relative to the truth when you look at the calculations and statistics. So 2 standard errors is a 95% confidence interval. But I just want to connect the 2 topics here. The reason we call it the residual standard error is because it's our typical miss of the residual, kind of your uncertainty, like 68% of the residuals are within this. That's your typical residual. But when we talk about the standard error of a coefficient, that is our uncertainty in a coefficient, because we can use that for the 68, 95 to build a 95% confidence interval. To build a 95% confidence interval for a coefficient, all you do is find that coefficient and go up 2 standard errors and go down 2 standard errors. What specific thing might we see in that interval that would tell us something about the significance of that coefficient? What specific thing might we see in that interval that would tell us about the significance of that coefficient? We might see 0. If 0 is in the interval, then we're saying it could be 0. The true coefficient could be 0, thus it is not significant. So 0 being in the confidence interval to estimate the true coefficient means that we would have a p-value above 0.05. Because tests for differences are 2-sided, confidence intervals are 2-sided too. They go out this way, and a test for a difference would test for a positive or negative difference, just like a confidence interval. Lots of kind of quick topics right there. Let's get to a big one right here, and let's interpret, okay, I love this one. Woo, okay. I like this one because, and I think it's alcohol going from like 0 to 100%. So, because you look at how much it changes, and pH also changes a lot too. Wines must not have that much of a pH scale. But, so let's interpret the coefficient of alcohol, which is, almost could get to some interesting stuff, but let's do it by the book. We have a multiple regression right now. We are interpreting the coefficient of alcohol. And we want to take a stab at this. Very specific interpretation here. We need to highlight some key parts. Some big questions right here. Anyone want to take a stab? Go ahead. Yes, I like that because we're in a multiple regression with all other x's being equal. That's a very important part. Go ahead. Try two wines that differ in their, so there we go. With residual standard sugar. And I'd probably say it's grams or something, or milligrams or something, the problem. So you probably want to say milligrams. I don't like crazy decimal stuff like this. I mean, your question might tell you a context for the problem, but it'd be easier to convert than trying to change the E numbers. Okay, I'll say the whole thing in 2 seconds. Yeah, got it. So, and then what do you need afterwards? You need one last sentence. Sir, no, you missed one thing though. Well, we start with that. So let me give you the full thing. You ready? So I usually say two wines that differ in their alcohol by 1, which is probably going to be 100% here, but we'll just say that. Two wines that differ in their alcohol by 1, but are identical in all other values of x. Now you could list them, but I'm usually all right with that. But are identical in all other values for the model, something like that. Does that make sense? Two wines that differ in their alcohol content by 1, but are identical for all other x values in the model. You could put a parentheses and list them if you want to be super nice. Parenthesis, density, whole sulfur dioxide, comma, free sulfur dioxide, comma, pH. Are expected to differ in their residual standard sugar by 2.489 milligrams, context we gave this, where the wine, and this was the one part you forgot, where the wine that has more alcohol is expected to have more sugar. The last part, the two parts in there are the standard for all interpretations for a simple linear, where you say two observations that differ in their x by 1 are expected to differ in y by whatever it is. Then you add in the last sentence to just ensure that people understand where the one that has the blank of blank is expected to have the blank of blank. Does that make sense? You guys know what I'm saying here, right? Sure. I'm going to say the whole thing one more time for everybody. It's great. So two wines that differ in their alcohol content by 1 are expected to, two wines that differ in their alcohol content by 1, but are identical in all other values of x for this model, yada, 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 are expected to differ in their alcohol content by are expected to differ in their residual sugar by 2.489, last sentence, where the wine that has more alcohol is expected to have more sugar, residual sugar. Good. Well, this one has no exponent right here. Yeah, that's why I picked that one. Good question. These other ones are to the positive. They're changing it. I think the scale is so very small on a lot of these. A lot of these are decimals, which makes it a weird problem. I wouldn't want to hint, this is not the data frame I used. I think the one I used is much more easier to understand. Yeah, it's nicer than this. It does say explicitly at the start. I don't want to, you could, if I told you what it is, you'd be like, oh, it's that kind of data, and start looking through the data frames. I don't know, if you construct enough models, you'd learn, you'd figure out the questions. Sure, do it with pH. Oh, it's good. It's not got decimals. Sure. Two wines that differ in pH by 1, whatever that is, but are otherwise identical in their values of X for density, alcohol, total sulfur dioxide, and free sulfur dioxide, are expected to differ in residual sugar by, and you could say negative 4.319 milligrams. I think the one I did on the test is positive. Yeah, it's positive. So you don't got to deal with that negative stuff. So I would say maybe negative 4.319 milligrams of residual sugar, where the wine that has a higher pH is expected to have a lower residual sugar. Now, you see, here's the big thing. If you're going to get like a 2-pointer, this is a bad explanation for things, especially for this. Wines with higher pH have lower residual sugar. Or you go back to step 2 and you say, for each 1 unit increase in pH, we expect residual sugar to decrease by negative 4.319. Now that's really bad too, because you're not comparing apples to apples. You're not doing the multiple regression part on that. That would almost, if this was a 10-pointer, that might be worth 1, because you didn't even acknowledge the multiple regression part of it, where we need to say with all other values of X in the model being equal. Does that make sense? That is key to a multiple regression right here. For the intercept right here, which is kind of illogical, it would have to be a wine that has no density, so the intercept would be interpreted among wines that have no density, no alcohol, no free sulfur, no total sulfur, and have a pH of 0. Is that pure acidity? That's base? Neutral is negative 6, positive 6? 7, something like that. I don't do this stuff much. I've seen it. Coca-Cola's like a 4, burn through your stomach. So completely neutral. You could interpret that. Among those wines, the predicted residual sugar is negative 2.267. This wine seems illogical, and also the residual sugar is illogical. This would probably be an extrapolation of the model, because it seems outside of the X bounds for which we see. Also, it makes a prediction that cannot exist. You can't have negative residual sugar. Sure. Oh, it's very similar to the, it's very, I go, well, one, because and so it's just generality. We'll do a 5 minutes generalities about the exam real quick, then we'll go back to questions. The exam is very similar to what you've seen with the practice exams. And so what I've done is the practice exams, I think is there 2 keys, 1 blank test, and 1 that matches a key. I pretty much put everything up that I have from collecting with working with Dr. Petrie on different things. So I could just put up 1 practice test, 1 key, but I have more stuff than that. So I'm like, here's everything I got. And so some of the stuff is kind of, doesn't have everything connected to it. So I'm sorry for that, but that's everything I have. And the test it'll look like just one of those. So you'll see, I think it looks just like a Dr. Petrie test, which I would hope, which is the whole intent for this, is that I'm supposed to teach this at the same level and the same way Dr. Petrie teaches it. If I start removing or adding too much, they'd be like, Brian, what are you doing? But if you think his tests are difficult, this test will be on the same level. If you think they're easy, it'll be on the same level. A lot of things are simply right or wrong. Not like all models, because, basically all models are wrong, but some are useful. Good knowledge right there. So, I mean, you really have that idea that in this test, we're trying to be, can you be exact with your knowledge? Once again, I think if you make a B on this test, great job. Like really, really great job. I put some stuff to distinguish the A's from the B's. If you make an A, wow. I mean, that's amazing. But remember, the take home is where you ensure yourself. You spend a few hours on the take home, you do everything precisely, because it's one thing if you can sit down and show the knowledge, but it's another thing if you can do the work. So we want to see that you have the knowledge and you can do the work. So try to, take both very seriously. Don't turn the take home in late. Probably everyone here I'm not speaking to. So don't turn, I would say 25% off per day late. So literally 2 days late and you're almost pointless. But still, turn it in then. Turn it in. I just have to get grades done over break, which everyone cross your fingers, everything gets graded, because I'll be doing a lot of grading too over break. Hey, I'll get mine done. So, what do you want me to do? What do you want to see? Oh, do the check. Oh, man, let's do the check regression on this. Oh, you've already seen it? Let's look at the multi, right? Yeah, let's look at the check regression on this. Is it asking me down here? Do I need anything? Nope. We fail all the linearity. All the linearity is trash. We could do the choose order on that to see what's going on. I think it's asking me here, something down here. Is it saying, no, it's just taking forever. Really? It should pop. Really? I don't think that's me. Come on. There it goes. As long as I've seen it taking a while. Oh, that's the 0 line right there. That's 0 right there. Everything bunched up on 0, where basically you have a whole bunch of wines that meet that criteria. So you usually see this as some break point in the model where everything is like hitting that, and you don't have any. You have a whole bunch of wines that exist at this, like, imagine you have a whole bunch of like red wines that have in them some variety, but they have a lot of the minimum values for a lot of it, the X's. So they're gonna bunch up down here, and you just get this like break point that they can't exist below. So you get that when you see a lot of limits on what you have, because that's all that is a limit, and it just comes through in that angle. Interesting though, very interesting. Major concerns. Number one prime concern on this, what do you think it is? I'm gonna go with my prime concern on this. What's your prime concern with this? Anyone? Equal spread's my moderate concern. I see it somewhat, but it looks like a wedge, which you don't want a wedge shape either. That's bad. Any pattern is bad, and that's pattern. My major concern would be what? You know, the normality, but is that like the worst normality we've seen? And the thing about this, this model overall, you know, is that the M multi? The model overall explains about 85% of the variation while rounding up. 85% of the variation is explained in residual sugars. Overall, that's really good. I'm very happy with this model. I want to see something real quick. I want to go to the summary. I want to look at the range of residual sugars, EX6, and what is the range of residual sugars? Yeah, that's our model. Look at the range from 0.6 to 23. And you know what? Let's look at it a better way. Let's go to a histogram of it. Okay. It's got a right skew to it. I want you to think about this. Our model is able to predict the residual sugar of most wines and has a general miss about 1. You're telling me when we make a prediction, we're usually only off by about plus or minus 1? It's pretty good. Does it sound like a practically significant model to you? Yes. When I talk about the typical miss, that is pure practical significance right there. Like, and also saying we understand about 85% of the variation is practical significance. You know, although p-value and r's are related, you know, r is actually like how much do we understand of it. So we understand a lot of this, and our predictions are really good. So, you know, someone could tell you how much sugar is in that wine if you told them a few things about it. If they're looking at the back of the label and they somehow were able to run this equation in their head, they'd be like, it probably has about 8 grams of residual sugar in milligrams. And then you'd be like, oh, it has 9. You'd be like, yep, I knew it. I mean, if they said 8 and it was 9, and on this scale, does that seem pretty close to you? Yeah. And do we usually, I don't even see that the typical miss is usually a problem here. That was a really good model. One of the best I've seen in a long time. Very useful model if you could predict within 1, especially with that scale. You think about how we look at this is the important things. What was I going to do next? The whole reason I kept adding in those variables is this. So I got it. It's got it. Not that bad. Not that bad. Let's take a look. Let's run it down here and see what our cutoff is. I'm going to round it 1 over 1, 1 minus 0.85. Does everyone know I'm using that? Huh, yeah, I should have guessed that. Of course, it's a bad omen. Okay, what did I just calculate with 1 over 1 minus 0.85 besides the mark of the beast? Not really. The cutoff for high variance inflation. And the whole reason I kept doing this from the start is I kept choosing variables I thought would be highly correlated, right? I kept grabbing at them, being like, oh, let's grab this one. Let's grab this one. I kept trying to put them in because I kept trying to take the highly correlated. And I got so excited by free sulfur and total sulfur because I was like, yes, they're both sulfur. So they're both going to explain the same thing. What's it mean for things to have high VAS? We said this earlier, I think. Yes. And more specifically, multiclinearity. You answered exactly what I was asking. More specifically, multiclinearity means that the X is explained in X. So multiclinearity instead of collinearity, explaining each other. Now that free sulfur could be explained by pH, density, and all the other X's in the model. It's like free sulfur is now the Y, and the X's of the model are explaining it. So the higher the variance inflation, the model gets confused on what to do with it. Because we keep saying, everyone brings pizza to the party, who do you invite, right? You're like, I don't know, they're all bringing pizza, they're all doing the same thing, why should I invite one person over another? So to talk specifically about all this right here, we didn't see it in our model. Why did we not see it, and how does that relate to the sums of squareds error? With the sums of squareds error reduction. Each thing we added to the model did what? Good questions. I thought you were going to go the quick way of saying it, but you went the long way, which I like. You said it reduced, it reduced the sums of squareds error in a way that was unlikely to have occurred by chance, you said, right? Correct. And to sum it up real quickly, it reduces the sums of squareds error in a significant way. Like, here's the big thing too. It is significant with the other variables in the model. What it does in explaining the sums of squares or reducing the sums of squares error is significant with the other variables in the model. So you don't want your variables to overlap on each other and do the same thing, because the model gets all confused. And when the model gets confused due to VIF, multicollinearity, what goes up? Now VIFs go up, but what does VIF means goes up? Our what's? VIFs go up go off of variance inflation, what goes up? If the variance inflates, the what inflates? Confidence interval, because confidence intervals are constructed from what? Variance is what squared? Standard errors. Standard error squared. You remember how, I think it was on one of your assignments, or we did it in class, in everyone class, I think, where, oh, it's so cool, we did it on the activity, where the variance was inflated by like, 6 or 7 times, right? Do you guys remember this in class? It was inflated 6 or 7 times, and then I went to the standard error, and then I saw that the standard error was inflated 7 times. It was like 0.10, and then it changed to 0.70. So what we see here is we don't really have much variance inflation. None of these are going to be really good to show this example with right here. I don't know. I can try to add in one more thing, but we don't have much else to add. Ay, ay, ay. 0.85 was the R squared of the model, very close to, I rounded it to 0.85. So that was used to calculate the cutoff for high variance inflation. That is the R squared of the model. What else? Sulfates, no, that's way too low. Fixed acidity and citric acid. Now let's go all out here, everybody. If we don't get something with this, we're done. Not literally, but. And citric acid, right? Okay. So we're going crazy. We're jamming this full. We're inviting everyone to the party here. Citric acid. We have a much bigger multiple regression right here. Now we have 93. Oh no, look at the adjusted R squared. Look at the adjusted R squared. I mean, that's good, but it's not doing what I want it to do. Because why is this good? Why isn't what does R squared adjusted mean adjusted for? Adjusted for how many variables in the model? Oh, look at the residual standard error. It went up, right? Because we were at 1 before, right? The residual standard error also has in it a penalty term. So now I'm actually a little bit like, we got something that's higher, not significant by itself. All right, let's look at the VIF. That one's going to have a decent VIF, right? Please work. None of them. None of them. Citric acid just, it does nothing. It's all bad. Okay, density. Cool. I can deal with this. Because density if you square 2, you get 4. So if the variance is inflated by almost 4, the standard error for density will be inflated by what? 2. So if we go back here to a simple regression and we make a density check model, this is just an example to show variance inflation. Don't worry, it's not that critical. Basically, I'm saying we'll move on from this immediately after. But what it means, okay, that's my x, right? Cool. I'm saving over my first linear. Sure. Okay, so what we should see here is in our multi-regression, the standard error of density is 1.678. So it should be about 8 point something. Oh wait, that's to the positive 1. So it should be to the 0. 8 point something to the 0 about. And standard error 18. I don't know if that turned out exactly. I hate when it changes the numbers. Is that correct? It's a smaller standard error than we're used to. So the whole point of this being, and I want us to look at, the problem with this is this. When you have high variance inflation, it inflates the standard errors. And this probably wasn't the best example. Usually you want to see more variance inflation than 4. High variance inflation is about 5 or 10. So we really didn't have much of a problem with our multiple regression with it explaining things it already explained. So when we have high variance inflation, it increases the standard error, which increases the uncertainty. How are we building confidence intervals for this model? And this is a key question again. To build a confidence interval right here, what would I do to make a confidence interval for the true coefficient of density in this model? Oh wait, no. How would I build a confidence interval for the true coefficient of density if I said build a 95% confidence interval? Kind of giving away the answer right there. 95% confidence interval for the true coefficient of density. Round it. Don't round it on the test. I rounded my numbers for you on the test. What is a confidence interval? It's the estimate, plus or minus. Well, we have an estimate of the coefficient, plus or minus. What? How many standard errors? Why 2? You're right though. Why 2 standard errors? 68, 95. So if that's 1390 and that's about 20, then it should be about 1350 to 1430. Does everyone see why I'm saying 1350 to 1430? Because if I round this to 20 and take a look, let's just run it down here. Confident M, and I say 1350 to 1430. 1350 to 1430. And that's just the decimal differences for not carrying out and rounding. You know, always a quick way to make a 95% confidence interval is to go plus or minus 2 standard errors, because it's 68, 95, 99.7. And we do this in our head a lot of times. It's a very common practice because you understand anything outside of 2 standard errors is uncommon. So our certainty, I mean, how certain are you that density is significant here? Very or I don't know. Very certain, yeah, because 0 is so far outside of that interval. Because if density is not statistically significant, it'd be the naive model. Things are independent, X and Y are independent when the naive model is true. Does that make sense? If the naive model is true, they'd be independent and it would have a slope of 0. Kind of keynote right there. That, you know, when you have the naive model, things are independent of each other. X and Y have no relationship in the naive because you have the mean of Y at all times. So the naive model is something that explains no variation. The naive model is our R squared of 0. That's just like baseline, nothing explained. It's what we use for the sums of squares total. The naive model is where the sums of squares total come from, and then we see, as we were saying, how much we observe being explained from what we would expect due to random chance. And that's where we can get things like, we'll do one last cool thing here, because when we talk about what could happen due to random chance, we have a really cool command here called possible regress, which we haven't seen in a long time. But these are the regressions we could get due to random chance. How does our regression look? Does our regression look like it would happen by random chance? No. Our line is way more sloped. By random chance, could our line go positive? By random chance, could our line go negative? If those points are randomly scattered about, do you think this happened by random chance? The p-value is 0, basically 0. Saying that the amount of variation we would observe being explained by random chance is somewhere down here. We have a ridiculous amount of variation being explained. Way, way better than random chance. Virtually impossible if this happened by random chance. Possible, but, you know, stats, all things are possible. Rest of it will be recorded and I'll publish it up. So you can see the rest where you left. Yes, exams. Probably want to start up about the 70-minute mark. Cool. Questions? We got another 30 minutes. We've covered a lot of good stuff tonight. Probably. Go. Oh yeah, let's do some interactions. Oh man. I'm gonna die. Okay, let's do an interaction. What was our two? We put the two top ones in here first, right? So let's grab density and alcohol, right? That'd be cool if they have an interaction. Oh, that could make some. I wonder. There's something I want to do with all this data right here. I'm gonna call this M interaction. So now we have an interaction model. It's not an interaction model yet. And now it is. Does everyone understand that's an interaction? You don't want to do this. That just carries through the interaction term. It doesn't carry through model hierarchy. We want to do this right here. So let's go ahead and run this. And we have our interaction model. And let's go ahead and write MIN and do that. And let's make a summary of it. And let's see if we had anything. We went fishing for an interaction. Did we get one? The interaction here is statistically significant. Yeah! What does that mean when interaction is statistically significant? How do the lines look? More likely to be. Slopes are changed when we look at the implicit lines, saying that knowing the effect of density would what? How density changes the residual sugar, what? Depends on alcohol. And especially for your assignment tonight, hopefully you haven't finished it up yet, if you want to write out the equations right here, you need to simply remember that when you plug in values of density, you would simply, if density was 2, plug in 2 right here, and then 2 times alcohol times this. This would lower, look at this, it's going to make the coefficient of alcohol negative. Does that make sense? So as density goes up, the coefficient of alcohol goes down. It makes the relationship weaker. Does that make sense to everybody? So, and as density goes up, the intercept goes up. So what we're going to see is at low levels of density, we'll have a lower intercept, and as density goes up, the line's going to go more down. So let's look at our implicit lines. Let's look at implicit lines. Actually, I like visualize model on this. Visualize model works for these. Should work. There it is. Okay. So let's look at as density goes up. Apparently, density doesn't have a wide range of values. Density looks to have values that don't go beyond 1. And I say that because when we look at the output right here, if density were to, I guess density is a value between 0 and 1, right? Maybe. Because if density were to go up to 1, that would be almost large enough to make this coefficient 0 and make it like the naive model. So does everyone see if density was 1, it would make the slope of the line flat? Does that make sense? Key question stuff right there. So we see as density goes up, going from small levels of density to larger levels of density. And although this line is just peaking out, we could imagine. So if you have a line like this that's just peaking out, make sure to imagine and kind of trace back in your head what's existing. But that is what we see right here. So let's take a look. Does this look like a statistically significant interaction? Yes or no? Very easy question. Statistically significant interaction because the p-value is below 0.05. So very, very, very statistically significant here. Model is statistically significant again. Ridiculous F statistic, 4,600 times more than we would expect due to random chance being explained. What else we got? Let's see. Explaining the interaction. When we explain the interaction here, we would say that at higher levels of density, the relationship between alcohol and residual sugar gets weaker. At higher levels of density, the relationship between alcohol and residual sugar gets weaker. So we're definitely seeing a weaker relationship that almost goes to non-existent. Had it become completely flat, then the densest of wines would have basically no effect from alcohol changing the residual sugar. So we would not predict any different for them. And yeah, because when you look at it, it's among wines that have small levels of density, we see that alcohol has a very strong positive association with them. And then we see even in the output to that, the slope gets weaker. Also, as we said, the intercept goes up, so they have a higher starting off point, a higher amount of residual sugar. And that's basically to say the densest of wines, regardless of alcohol, just have a ton of sugar in them. Does that make sense? Makes sense, right? The densest of wines, regardless of alcohol, mostly just have a bunch of sugar in them. But then the less dense wines, generally the more alcohol they have, the more sugar they have in them. Are there any wine drinkers in here? Seriously. You know what I'm talking about, some ice wines or dessert wines, right? They're generally higher alcohol content and they have more sugar, right? So look at this. When we have lower density wines, when it has higher alcohol, it generally has more sugar. So it literally goes by what we know. Wines are, you know, it's data, it's real world stuff, so we like it. Okay, so that's got the interactions right here. That's an interaction plot, interpreting it. Please ask any follow-up questions if you have them about interaction plots. Kind of cool stuff. Keep going another 20, 30 minutes. Go ahead. More interactions? Oh, no. I think you're talking about choose order, right? Yeah, we can look at a choose order on this. Let's do a choose order. So let's do the choose order. I love the choose order command. So you're probably talking about the polynomial looking for, yes, higher order relationships with choose order. You could do a three-way interaction. You could do a four-way, but let's not do that. I will not do that to you on the test. I do not want to interpret them either. I have and can. We've all talked about that. Not fun, right? Let's not do that. If I don't make you guys do it, then I don't want to do it. So let's do a choose order right here. Nice and fun stuff with the choose order. With our choose order, we want to go to our M model just for our simple model and let's take a look at what we got going on right here. I am guessing that the choose order is going to come back with the first one right here. I think the choose order is going to be the first, and why do I think that? Because it looks like a bunch of wires. You guys ever see like spindled wires? Because there's not a whole ton of differences between 2 to 6. Let's look at the choose order command right here. This is good for your take home, especially too. Oh, interesting. This is a fun one. Step number 1. Highest one is what? 6th. Step number 2. Subtract 0.005. Just so everyone can see exactly. Double click this, command copy. Go down here, paste, minus 0.5, put that there. That's interesting. The answer to the question is, choose order number what? Aha, 4. You can't go any lower than that. That's your bar. Now, explicitly, especially for the test and for your take home, you don't want to go to higher stuff. Model, we do want a complex or a simple model. What do we generally want? We generally want a simple. It's like I say to you guys, if you have one friend who can take you 97% of the way to California, or 100 friends who will take you 98% of the way, what would you prefer? What do you say? One friend will take you 97% of the way. That makes more sense, right? Because you take the simple car trip over like, oh, I'll bring you an hour closer, not even an hour, like 20, 30 minutes or something closer to California. So I'll figure out the rest. I'll figure out the rest with other stuff. Maybe I'll try to call other friends. But these 99 extra friends aren't doing that much. And that's what will show up in the adjusted R squared. And that's why we do this. That's why we're willing to kind of, and I know the adjusted R squared already has in it its own compensation for the extra polynomial terms being added to the model. But we're also saying like, they're basically the same. I mean, at that point, you could make a confidence interval for them and say these adjusted R squares are virtually identical. Why are we going to change it? But look, even I said, and I was so close to being right because these are close. But apparently the 6 to the 3rd, these extra bends with the blue ones are not showing up. See how the red and the green are different? They don't have that downward bend at the end. That's that extra bit of variation that is keeping us, because that's why these are just not quite good enough And then the black line sticks out like a sore thumb because the black line is vastly different in its ability. This is friend saying, I'll say, take you 68% versus a friend saying 76%. And so you're saying, okay, I'll take the 76%. That's a huge difference to me. So once again, what we did is we found the highest R squared, then we subtract off 0.005, and then we only go to simpler models. Only. Question? So let's say, well, if this was 0.766, this would be our first initial choice. And also, especially for tonight's homework, when you enter in the poly includes the model hierarchy, which shows up when you do the checker graphs. The checker graphs will show the fit for all the extended models. So when you do poly, poly variable, 4, it'll include all the lower order poly terms and the simple linear. Question? So this one, let's look at a different one that doesn't do what we saw here. Let's take, what's our simple right now? Our simple model, where is it at? There it is. I'm going to change this. Oops, missed it. There you go. I'm going to change this. Is density capital? Nope. I'm going to change this to density, and now I'm going to run it again for this one. Let's see what goes on here. Wait, is this the same one? Looks about the same. Yeah, it's the same. How did that happen? Did I not run this? Maybe I didn't run it. No, I ran it. There it is right there. All right, let's take volatile acid. I'm going to try to make a different one right here so we can just see. And, okay, there it is right there. I've created my linear. Now I'm doing a choose order on it. And let's take a look. It looks like the first order is not going to be the best. I'm thinking somewhere around, see that bend in the green one that's not present in this one? Of course, then it bends. I'm tossed between the 3 and the 5. I kind of look at this to kind of get a gauge what's going on. Let's see what's happening here. What's the highest R squared adjusted? 5 is the highest. Do you see the two focal points I even saw in the graphics with the 3 and the 5? How they're kind of the high points between the two. But our highest is what we do first. I'm just doing extended knowledge with me looking at the graphic first. If you want to do this, just buy the book. Just go look at the R squared adjusted. Step number 1, find the highest R squared adjusted. Then take that highest R squared adjusted, bring it down here, and do what to it? There we go. Called it. Why'd I call it? I thought it would be this, and it is. What's the answer to the question? The answer is 3. Once you decide upon 5, what is the only direction you can go? To simpler models, if that's what you mean by that. To simpler models, yes. You can only go down in the choose order. Yeah. It's confusing, right? Yeah. Those are, and I want to make that clear. So you're exactly right. You can only go to the lower order models as shown here by what I've highlighted. I want to make that clear. 6 is of no consideration to you. You only do this step one time. You only say, here is what we have. And this is I don't even know if this is statistically significant. Doesn't matter. This is just an example. So what we have here is that the 5th order is our model. Very low adjusted R squared. At least it's not negative, because adjusted R squared can be negative. So 5th is our 1. Then we subtract off 0.005. Then we go to one that meets that standard. This is above this number. That's why we've stopped there. Imagine 0.007 being between here. You cannot go past that middle line right here. That thing right here is that line. That's 0.007 blocking you from going up. Now, this could be higher. Like, let's say if this was 0.008, which weird things happen. But if this was 0.008, would 1 be our choice? If 1 was 0.008, would we choose 1? Yes or no? Yes, we would choose 1. Is that clear? And I think all but the first class, I thought of the best way of doing this. We became a computer. It was my computer class. It's like the last class, I think. There we go, computer. This is how a computer would look at this. Step 1, find highest R squared. Highest R squared is order number. Computer stuck. 5. Subtract off from that 0.005. Here is my standard. Does model 1 meet my standard? Does model 2 meet my standard? Does model 3 meet my standard? Choice is model 3. That's literally, if you were to code this in, as students have done, that's literally what you're doing. Because it's weird if we say like go down the order, because some people get confused. They're like, oh wait, if this is 0.008, can I choose it? And the answer is yes, because what's always better? What's always better? Simpler is always better. Oh yeah. Oh yeah. Well, how's it determined?
I mean, what do we use this for?
What you would use this for is if you have nonlinear relationships, because this is going to help clear out some of the problems in your residuals. You know, we get like a bend in the residuals. So this is kind of the idea of almost fine transformation. Fine transformation and choose order are one in this, not one in the same, but they're fine transformation. Here's the problem with fine transformation. And this is a very good applicable thing, which you should know, especially if you want to do business analytics, you got to know this. Fine transformation is going to take away a lot of your interpretation of the data. But the thing is, it's going to fix a lot of like the spreading out, especially with like a log-log transformation. You got highly skewed data, log-log transformation is going to pull it back to a normal. So fine transformation will often bring normality to data, which is good, which could bring normality to residuals. Where choose order is going to fix oftentimes linearity problems to where the model has linearity. So you've got two things. Fine transformation might bring normality to residuals. Choose order might fix a linearity problem, because what are we doing with choose order? We're allowing the line to bend, which you can do with a transformation too, because you could transform it with a squared term or a square root term, and you're kind of doing the same thing. A lot of transformations might do what the choose order command does, and you might even choose to do a transformation, because if you transform, you limit the variables in the model, but you take away interpretation. But with choose order, you increase the variables in the model, but you kind of reserve some interpretation, so we can talk about a parabolic kind of curve to the data. You remember with the bulldozer data set where we said it levels out in the 70s and goes back up in the 60s? You got a little easier interpretation with your choose order, and you can fit non-linear relationships. But with the transformation, you lose a lot of interpretation. It becomes really a predictive model when you start transforming. You can interpret, but it's a lot harder. But you're looking at more of a predictive model with transformations. You preserve your interpretation for a descriptive model with choose order, because then you can talk about what we see with the lines a lot more. You don't really have good, strong coefficient interpretations, but that's a really great question. Does that all make sense?
Yeah, I think so.
It's really, think of it as a fixed sort of linearity, especially when you see it. If you see unexplained variation in the residuals, start running a choose order on each of your x's in the model to see if any of them can pick up on it. Or even save the residuals in your model, feed the residuals back in, and run a choose order on your residuals. We didn't do that, but believe me, did any of you guys get excited about business analytics? I love analyzing data. Do it. No, it's cool. Don't worry. Maybe 10 years, like 5-10 years from now, you're like, yeah, data, Brian. You're like, when you find stuff in data, especially when you've been looking in it, like I'll say this really, really quickly, and we'll do like 1 or 2 more questions. My Stat 201 students just took their test, and I found out that 45% of the variation in their test scores are explained by what they do on my Pearson. Now, I'm kind of bummed, because that means 55% is explained by something else, which I do not know what it accounts for. My residual standard error was about 8. Which means if I were to predict my 201 student scores from my model, I'd be off by about 8, which my girlfriend said to me, well, that's basically a letter grade. And I was like, shh, it's all right. Like, I mean, it gives me some insight, but there's still a lot of variation, and she literally said it to me. I said, my R grade's 45%. And she knows enough to say, well, that means there's 55% you don't understand about the grades. Does that make sense? Like, I don't know. She teaches me science, and I teach her statistics. And it's exciting, especially as an instructor, to say to my students, you know, and that's one thing we should mention here. I'm throwing out little things real quick at you guys. You gotta watch out, because these are test things every once in a while. Every little aside I go on has pretty much had a little testing. You should rewatch the video, because I've said a few things that are very test related in my asides. Hint, regression is not a physical law. You can't talk about, you know, if I say to a student, oh, if you do more of my Pearson work, your test grade will go up. That's not how regression works. You can't change an X in the model and then say this will happen to this if this happens. The whole thing about our regression is comparing X's in the model to say observations in the model that differ by this are expected to differ by this. Not to say if an X in the model changes to this, what will happen? It's not like that. We look at the famous example we had in class. This is the last bit of this side before we take another question. The famous example in class was with body fat and weight, where we saw that two people who are of equal everything, like arms, waist, all this stuff, height, and if somebody weighs more, what was their body fat? Everything being equal, all other x's being equal, two people who differ by 1 pound, the person who is heavier is expected to have what body fat? Lower. And that's not how the real world usually works, right? Because if you say, oh, well, if you gain weight, you'll have less body fat. What kind of weight are you gaining? You can't, it's not a physical law. Regression is not a physical law. It's saying, what do we observe with people in this model? And if the model is a good reflection of reality, then if our model is a good sample of reality, then the real world will act like our model. Does that make sense? If you take two people in the real world who differ by weight in one, but have all other x's identical, we would expect the person who weighs more to have less body fat. Because what do we know about muscle versus fat? Muscle is what to fat? Muscle is heavier, right? So if you weigh more, if there was someone who was exactly the same everything as me, but weighed 40 pounds more, would they? Well, they couldn't. They'd have to be like more compact, right? Does that make sense? And I think that is the prime example of how regression is not a physical law. Because you can't say, go gain weight and you'll lose body fat. That's not how it works. It's about making a reflection of reality with our model, and then you talk about two things that differ in the model, and if the model is a good reflection of reality, it would be the same for two things in the population. But it's not saying what will happen if someone changes. That's not regression. That's pure trick question nonsense. Regression is not a physical law. It's good aside. It's very important. Someone at the test is going to be like, ooh, ha, ha, ha. I hope. I've definitely dropped some knowledge bombs for the test in here. What else we got? Let's do one more thing here. What else? What do you guys want to see? What we're going to do? Talk about. You better watch out. You're going to be taking the test, and you're going to hit that question. You'll be like, do, 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 do. And then you're going to get your test back and be like, oh, no. Someone in my office is literally going to do that. They'll be like, this is the one you were talking about, right? This is the one. I guess let's take a few final finish up questions. I think we covered everything. Front, back, whatever you want. Make sure it's standard paper, print it, do whatever you want. Type it, print it, whatever you want. Front, back, put things properly. Looks like you've got like a primo one you're ready with. Do what? Yeah, well, and the thing is, a lot of times when you build the cheat sheet, you really learn it. So you're like, this is what I need to know. So remember, cheat sheet tests are hard tests. More questions, ask some more questions about the test. I think what we didn't cover very well. I think there's a few things on the take home which are hit on a little bit harder that maybe I didn't hit upon tonight that, generally if it's a little thing, it might be on the take home. I think there's only one thing that I wish was on the test. It's pretty, I don't know. I don't want to go back and start rewriting the test. I think there's only one topic on it. It's so small. It's just, I don't want to say what it is. It's so small. It's such an easy concept that you're like, why didn't you put that on there? Anyone got to guess what it is? I'll give you one guess. You got to raise your hand. I'll call on you. You got to give one guess. I'll tell you if it's on there. It's a concept. No guesses? You're like, I don't got to study that. It's such an easy concept. Raise your hand. Any guess? Huh? Let's take a guess. It's not on the test. It's not on the take-home, I don't think. We didn't talk about it tonight. Don't not study things we didn't talk about. I would say we covered 70 to 80% of the test. You guys feel pretty good? A lot of stuff was covered. Questions? It's not that. So I'm not going to comment more. He said, is it mosaic? And that's not what I was thinking about, but I'm not going to comment about that. We didn't talk about mosaics tonight. We talked about ANOVA tonight, kind of. ANOVA is more of the comparison of multiple means, which we did 2 means, so definitely know that stuff. So, what else? Anything else? More questions? Definitely, I think the bulk of the test is over, simple linear, multiple regression, stuff like that. There's interaction stuff. The test is really built around, this is one of the earliest I've ever made a test and made the key. My girlfriend has a big test on Monday and Friday, and she literally spent all the day studying, and I spent all today working. Do what? Oh, thanks. So, whatchamacallit? See, if you're boyfriend, girlfriend, you should work when your girlfriend or boyfriend works, because then you get free time together. That's the way it works. It's like you work, and then you get free time. But, whatchamacallit? So let me just tell you guys the format real quick. It's 7 questions. I think I make 3 statistical there's 4. They're really, yep, it does follow the same data set the whole time. So I encourage you, if you want to study, start making models and stuff with a data set. You might stumble upon the one I made. So start interpreting and figuring out how to interpret, send it around to your friends. I mean, I'm encouraging everyone just to start figuring it out. You might, who knows? It'd be funny if someone came to me like, Brian, I literally interpreted the exact same thing that was on the test. So you're dealing with data sets that we will see in class, nothing too strange. Data set kind of makes sense. And 4 models in it. Starts off with an associate command, goes through linear, goes through multiple, goes through an interaction. 7 questions, but it's not like I said, my girlfriend was like, 7 questions? Why'd that take 6 hours? And I was like, because they each have like 10, 15 parts. It's all little things. It's all little things, you know? Like, do you understand VIF? Where are you going to see VIF? The associate, the simple, the multiple, or the interaction? Where are you going to see VIF at? Uh-oh. Which one? The multiple. So you'll see some VIF in the multiple. That's got it. It's like 9 pages. It's like a 9-page test. You guys are free to go. Ask questions if you got them. I'll stop the recording for the review. Explosions. Oh, you see, look, we are recording here. Oh, watch nothing I've recorded. That'd be, yeah, I'm still recording here. I'll stop it in here in 2 seconds. End meeting. End meeting.